configuration and will generally be a compound. But that's not true of all metals, because some metals are noble and some metals will resist this decomposition. And so we expect to find the noble metals free in nature, and we do find them that way. And we find gold and silver in nature so that we can just pick it up, nuggets of gold and nuggets of silver. Also, we find copper in nature. And for instance, I have here in my hand a piece of copper that dripped out or was found just running outside of a mountain in Alaska. An explorer up there, a friend of mine, picked this up, just picked it up as a solid hunk of copper. It's deteriorated a little. It has a greenish color on the surface. You notice that if you look in this edge of it, it has little shiny spots. That's the copper color where it was sawed in two. But the early Indians in this country took this particular material and hammered it out. They found that it was ductile. They weren't Amoses. They could make things out of trinkets, ornaments, tools. And so early man could find this particular material. And he could find another material in nature that just happened to be there and didn't deteriorate very rapidly. And strangely enough, it's one of our most modern alloys. And what he found was stainless steel. And guess where it came from? The heavens. The metallic meteorites that came in, and they were iron nickel alloys. And they didn't deteriorate very rapidly, and so he could find that on occasion. And he found the gold, and he found other things, but the most intriguing thing was that he learned, and we're sure he learned by accident, to refine some of these materials. So let's look at how we would imagine he'd do this. Let's start with something as simple as lead. Lead will deteriorate very easily and very rapidly in the atmosphere over long periods of time. And one of the compounds it forms is lead sulfide. If we take lead sulfide and just heat it up in the air, the sulfur that's in the lead will combine with the oxygen that's in the air and make sulfur dioxide and leave behind lead. So it's certainly conceivable that if early man could find some lead sulfide, and this was just a kind of a dirt, then he could take that particular kind of a dirt and say, okay, I'll use it to, let's say, build a dam around my fire that I'm making. And the fire heated the material up, drove off the sulfur dioxide, and he would have little pools of lead that would gather around. And he picked it up, and all of a sudden he'd have a metal, or maybe an impure metal, maybe an alloy, that he accidentally refined. Well, fortunately, our forefathers were very good observers over the long years, and they learned how to do this trick so they could reproduce it and do it over and over and over again. And so the process that he used has come to be known as smelting, the use of high temperatures and molten materials to get chemical reactions to occur that will reduce the ore to the metal. Ore? Hey, have we run into another word we don't know? What's an ore? Do you know?
What's in a rowboat?
Anybody? What's an ore? If you go out and pick up a handful of dirt, is it an ore? Now, let me tell you something. If you look at the crustal abundance of the elements in the earth, and we'll do that a little later, we'll see what the percentages are, but let me just tell you that if you looked at that, you'd find that a very abundant metal on the face of the earth, in the crust of the earth, is aluminum. And if you had a little piece of property, 1 acre big, and you took all of the soil 6 feet down, and it contained the average aluminum content that was in the crust of the earth, you'd have $500,000 worth of aluminum. So why isn't everybody in California digging up their backyard? There must be a reason, right? And the reason is that material is not an ore. And we define an ore as something that from which we can take the metal at a profit. And if you can't take it at a profit, then we don't call it an ore. As soon as we learn a technology to take that material that's in your backyard with the aluminum content it will have and squeeze it out at a profit, then people will be digging up their backyards, all right? So man learned to take ores, to identify ores, and to put them through the processes that are going to give him different kinds of metals and alloys that he could use. And so, for instance, he could refine copper sulfide just as he did the lead sulfide. He could also take copper oxide, and if he got his fire hot enough, since he was generally burning carbon, he would have a reduction of the oxygen that's with the copper, and it would go off as carbon dioxide and leave behind copper. And he must have learned to do that in small pits, and later on in this week we'll describe how we do this under control in big modern furnaces. But we know that early man was doing this sort of thing. And not only that, he even learned to reduce iron. And probably the first iron he ever made was by taking this most abundant material. The third most abundant element on the face of the earth is iron, and so it exists as iron oxide generally. We can find it in that form, and it's a beautiful red ore. And if he made a brick or a fireplace out of that material and he got his fire hot enough, then he could reduce the iron oxide to elemental iron just by the reaction of the carbon with the oxygen. So it passes off as a gas, and he has left behind the iron. However, all of this material is going to be in the solid state. That says he didn't have to liquefy it. So he really didn't smelt the material per se. He didn't get it liquid in this particular case. But he got a sponge iron, a porous piece of iron, that he found if he heated it up and he hammered it together, it would weld together, it would be in one piece, and he had then a piece of elemental iron. And we know he did those sorts of things in the early days. Well, that's a practice that we have to learn a lot about. We haven't moved too far up the scale from some of these things, but we are capable of taking these ores that are on the face of the earth now and converting them to everything that we want, or everything that we think we want. And we say, since we can do that, then a lot of the material, and we don't have anything to worry about, we're in. We've got it made today. Well, I'd like to show you a slide of what we do in the use of some of the metals that we have. And in this slide, what we see is we see the crustal abundance of the earth not represented, but the imports that we have of this particular material. And in the imports that we have, we find that things like cobalt and manganese, we import 100% of these materials. This is not an abundant nation in those particular materials. I guess one of the first things we need to know is, do we really need this stuff? And so let me tell you one thing, that we can't make a pound of steel without manganese. So we have to have manganese, and yet we import 100% of it into this country today. But if you look at the chart, you'll find out that in reality, then we get all of the different materials that we want imported. We get a sizable import of all of these particular materials. We wouldn't have to worry about this too much if it wasn't for something that's called international strife. We have problems with other countries. Everybody doesn't want to share it. But let me just give you one little illustration. Cobalt, a material that we can't do without because we use it in high temperature turbines, and we use it in medical implants, and we use it in a lot of different places. And we have cobalt in this country that's mineable, not many places, but at least one mine. It happens to have a natural preserve around it. We have a forest around that we would like to preserve. We'd like to keep that forest just like it is. And so we don't mine the cobalt here because we don't want to upset our balance. So instead we get our cobalt from another country. And what we're saying sort of is, we'll upset their balance. We don't really care, right? And then we'll import it. Well, that's philosophical now, and it says that this field of metallurgy is going to come into international politics, philosophical reasoning of, say, controlling our environment and things like that. But in the next slide, we would find out that there's something else that we have to examine, and that is how our materials will look relative to, let's say, what we really need in this country and what we have, and what we really need in this country and what Russia has. And so on the charts that you see on the board now, that particular illustration is given to you. And it looks like in a lot of our strategic materials, a lot of our critical materials, Russia has a much better chance of maintaining their level than we do in some of these things. Well, where do they really come from? Where do all of these things really come from? In the next slide, what you will see is that, let's say we looked at Africa, we find out that we get many of our critical materials and our strategic materials from Africa. We get them from Australia and Indonesia and lots of places in the world, but here we have a country that we have to be in tune with one way or the other, because we get so much of our natural resource from it that we absolutely need in the metallurgical field. And we say, well, maybe we won't be using as much in time to come. So what we really need to do is we have to look at our needs in the future. And if you look at these particular plots, what you see is what the supply and demand looks like in this country projected into the year 2000. And it doesn't make much difference what you look at, whether it's going to be chromium or zinc or whatever. You find the curves look just about the same. That is to say, you find that our use of these materials is so great that in the future we're just not going to have any of the material around. We're not going to be able to put our fingers on it and say, hey, that's something that we've got plenty of. Now, there are a few things that we do have plenty of, but in most of the metallic materials we have this as a problem. Well, we have a problem now, and the problem is, what are we going to do about all of this? You know, most people don't know what stealing is. Most Americans don't know what stealing is. If you think you have an abundance of material and you overuse some of it, or you use some of it, you don't pay much attention to the fact that you are ridding the supply. For instance, it's hard to think that you have a water shortage if you were standing under the Niagara Falls, right? But if you were in the middle of the Sahara Desert, you would say, gee, the earth must have a water shortage. If you go to an acre of corn, or let's say 100 acres of corn, and it's ready to be picked, and you'd like to have a piece of corn, and you break it off the stalk to eat it, it's not your field of corn. You don't say, I'm stealing. You don't think about stealing. It's so much there, right? Well, the fact of the matter is that what we are doing today is we are consuming materials. Actually, you and I, every man, woman, and child in this country demands the production of 112 pounds of material a day in the form of concrete, wood products, paper, pulp paper products, building materials, metallic materials, and so forth. 112 pounds a day. Every man, woman, and child in this country. A demographer at the University of Ohio, Chuck Overby, has computed that if the rest of the world consumed or demanded the production of materials at that rate, if every other nation did that, and if the population of the world continued to grow at the rate it's growing, in 1,500 years we would consume 1/2 of the mass of the earth.